Learning objectives. In this chapter, the user would learn the following aspects of programming embedded system: programming languages, use of high-level languages, C, OOPS, Java for embedded systems, programming and runtime environment, program validation and testing. Introduction to Object-Oriented Programming. Object-Oriented Programming, OOP, is a programming paradigm that represents the concept of objects that have data fields, attributes that describe the object, and associated procedures known as methods. Objects, which are usually instances of classes, are used to interact with one another to design applications and computer programs. The object-oriented approach is considered a logical extension of good design practices that go back to the very beginning of computer programming, rather than being revolutionary as claimed by some proponents. Object orientation is simply the logical extension of older techniques such as structured programming and abstract data types. An object is an abstract data type with the addition of polymorphism and inheritance. Rather than structure programs as code and data, an object-oriented system integrates the two using the concept of an object. An object has state, data, and behavior, code. Objects correspond to things found in the real world. The goals of object-oriented programming are increased understanding, ease of maintenance, ease of evolution. There have been several attempts at formalizing the concepts used in object-oriented programming. The following concepts and constructs have been used as interpretations of OOP concepts: co-algebraic data types, abstract data types which have existential types, allow the definition of modules but these do not support dynamic dispatch, recursive types, encapsulated state, inheritance. Records are basis for understanding objects if function literals can be stored in fields, like in functional programming languages, but the actual calculi need to be considerably more complex to incorporate essential features of OOP. Several extensions of System F that deal with mutable objects have been studied. These allow both subtype polymorphism and parametric polymorphism, generics, classes and objects. A class is used to specify the form of an object, and it combines data representation and methods for manipulating the data into one neat package. The data and functions within a class are called members of the class. Concept: class member functions, class access modifiers, constructor and destructor. A member function of a class is a function that has its definition or its prototype within the class definition, like any other variable. A class member can be defined as public, private, or protected. By default, members would be assumed as private. A class constructor is a special function in a class that is called when a new object of the class is created. A destructor is also a special function which is called when created object is deleted. The copy constructor is a constructor which creates an object by initializing it with an object of the same class, which has been created previously. Data encapsulation is a mechanism of bundling the data and the functions that use them, and data abstraction is a mechanism of exposing only the interfaces and hiding the implementation details from the user. All C++ programs are composed of the following two fundamental elements: program statements, code. This is the part of a program that performs actions and they are called functions. Program data. The data is the information of the program which is affected by the program functions. To make parts of a class public, that is, accessible to other parts of your program, you must declare them after the public keyword. All variables or functions defined after the public specifier are accessible by all other functions in your program. Abstraction. Let's take one real-life example of a TV which you can turn on and off, change the channel, adjust the volume, and add external components such as speakers, VCRs, and DVD players. But you do not know its internal details. That is, you do not know how it receives signals over the air or through a cable, how it translates them, and it finally displays them on the screen. Thus, we can say a television clearly separates its internal implementation from its external interface, and you can play with its interfaces like the power button, channel changer, and volume control without having zero knowledge of its internals. Benefits of data abstraction. Class internals are protected from inadvertent user-level errors which might corrupt the state of the object. The class implementation may evolve over time in response to changing requirements or bug reports without requiring change in user-level code. Base and derived classes. Access specifier is one of public, protected, or private, and base class is the name of a previously defined class. If the access specifier is not used, then it is private by default. Access control and inheritance. A derived class can access all the non-private members of its base class. Thus, base class members that should not be accessible to the member functions of derived classes should be declared private. Types of inheritance. Single inheritance. When a single derived class is created from a single base class, then the inheritance is called as single inheritance. Hierarchical inheritance. When more than one derived class is created from a single base class, then that inheritance is called as hierarchical inheritance. Multi-level inheritance. When a derived class is created from another derived class, then that inheritance is called as multi-level inheritance. Hybrid inheritance. Any combination of single, hierarchical, and multi-level inheritances is called as hybrid inheritance. Multiple inheritance. When a derived class is created from more than one base class, then that inheritance is called as multiple inheritance. But multiple inheritance is not supported by .NET using classes and can be done using interfaces. Public inheritance. When deriving a class from a public base class, public members of the base class become public members of the derived class, and protected members of the base class become protected members of the derived class. A base class's private members are never accessible directly from a derived class, but can be accessed through calls to the public and protected members of the base class. Protected inheritance. When deriving from a protected base class, public and protected members of the base class become protected members of the derived class. Private inheritance. When deriving from a private base class, public and protected members of the base class become private members of the derived class. Uninheritable class. The sealed class has no subclasses, so it can be easily deduced at compile time that references or pointers to objects of that class are actually referencing instances of that class and not instances of subclasses. They don't exist. Or instances of superclasses. Upcasting a reference type violates the type system. Subtype polymorphism. Because the exact type of the object being referenced is known before execution, early binding or static dispatch can be used instead of late binding, also known as dynamic dispatch or dynamic binding, which requires one or more virtual method table lookups depending on whether multiple inheritance or only single inheritance are supported in the programming language that is being used. Interface. In object-oriented languages, the term interface is often used to define an abstract type that contains no data or code but defines behaviors as method signatures. A class having code and data for all the methods corresponding to that interface is said to implement that interface. Furthermore, a class can implement multiple interfaces and hence can be of different types at the same time. Overriding. An interface is hence a type definition. Anywhere an object can be exchanged, for example in a function or method call, the type of the object to be exchanged can be defined in terms of its interface rather than specifying a particular class. This means that any class that implements that interface can be used. For example, a dummy implementation may be used to allow development to progress before the final implementation is available. In another case, a fake or mock implementation may be substituted during testing. Such stub implementations are replaced by real code later in the development process. Many object-oriented programming languages permit a class or object to replace the implementation of an aspect, typically a behavior that it has inherited. This process is usually called overriding. Overriding introduces a complication. Which version of the behavior does an instance of the inherited class use? The one that is part of its own class, or the one from the parent or base class? The answer varies between programming languages, and some languages provide the ability to indicate that a particular behavior is not to be overridden and should behave as defined by the base class. For instance, in C programming, the overriding of a method should be specified by the program. The version of a method that is executed will be determined by the object that is used to invoke it. If an object of a parent class is used to invoke the method, then the version in the parent class will be executed. But if an object of the subclass is used to invoke the method, then the version in the child class will be executed. Some languages allow a programmer to prevent a method from being overridden. Data typing, polymorphism, overloading. Data typing. The basic types can be modified using one or more of these type modifiers: signed, unsigned, short, long. Variables are reserved memory locations to store values. This means that when you create a variable, you reserve some space in memory. You may like to store information of various data types like character, wide character, integer, floating point, double floating point, boolean, etc. Based on the data type of a variable, the operating system allocates memory and decides what can be stored in the reserved memory. Polymorphism is the ability of an object or reference to take many different forms at different instances. These are of two types. One is the compile time polymorphism and the other one is the runtime polymorphism. Compile time polymorphism. In this method, the object is bound to the function call at the compile time itself. The method overriding is an example of runtime polymorphism. You can have a method in subclass which overrides the method in its superclasses with the same name and signature. Runtime polymorphism. In this method, object is bound to the function call only at the runtime. For every function call, the compiler binds a call to one function definition at compile time. This decision of binding among several functions is taken by considering formal arguments of the function, their data type, and their sequence. The word polymorphism means having many forms. Typically, polymorphism occurs when there is a hierarchy of classes and they are related by inheritance. Polymorphism means that a call to a member function will cause a different function to be executed depending on the type of object that invokes the function. The compiler looks at the contents of the pointer instead of its type. Hence, since addresses of objects of try and rect classes are stored in star shape, the respective area function is called. As you can see, each of the child classes have a separate implementation for the function area parenthesis. This is how polymorphism is generally used. You have different classes with a function of the same name and even the same parameters, but with different implementations. Virtual function. What we do want is the selection of the function to be called at any given point in the program to be based on the kind of object for which it is called. This sort of operation is referred to as dynamic linkage or late binding. Pure virtual functions. We can change the virtual function area parenthesis in the base class. The equal to 0 tells the compiler that the function has no body, and above virtual function will be called pure virtual function. C++ allows you to specify more than one definition for a function name or an operator in the same scope, which is called function overloading and operator overloading respectively. An overloaded declaration is a declaration that had been declared with the same name as a previously declared declaration in the same scope, except that both declarations have different arguments and obviously different definition implementation. Function overloading, operator overloading. Function overloading. You can have multiple definitions for the same function name in the same scope. The definition of the function must differ from each other by the types and or the number of arguments in the argument list. You cannot overload function declarations that differ only by return type. Operator overloading. Operators can be extended to work not just with built-in types but also classes. A programmer can provide his or her own operator to a class by overloading the built-in operator to perform some specific computation when the operator is used on objects of that class. The three basic rules of operator overloading. Whenever the meaning of an operator is not obviously clear and undisputed, it should not be overloaded. Instead, Provide a function with a well-chosen name. Always stick to the operator's well-known semantics. Always provide all out of a set of related operations. Programming languages. A programming language is a formal constructed language designed to communicate instructions to a machine, particularly a computer. Programming languages can be used to create programs to control the behavior of a machine or to express algorithms. The description of a programming language is usually split into two components: syntax, that is form, and semantics, that is meaning. Some languages are defined by a specification document. For example, the C programming language is specified by an ISO standard, while other languages such as Perl have a dominant implementation that is treated as a reference. Many free C compilers are available for a wide variety of development platforms. The compilers are part of IDEs with ICD support, breakpoints, single stepping, and an assembly window. The performance of C compilers has improved considerably in recent years, and they are claimed to be more or less as good as assembly, depending on who you ask. Most tools now offer options for customizing the compiler optimization. Additionally, using C increases portability since C code can be compiled for different types of processors. The C language is standardized, and there are a certain number of operators available that everybody knows and loves. However, many microprocessors have capabilities that are either beyond what C can do or are faster than the way C does it. For instance, the 8051 and PIC microcontrollers both have assembly instructions for setting and checking individual bits in a byte. The C programming language is perhaps the most popular programming language for programming embedded systems. C is not the only language used by embedded programmers. There are 4 other languages: Assembly, C++, Forth, and ADA. In the early days, embedded software was written exclusively in the assembly language of the target processor. This gave programmers complete control of the processor and other hardware, but at a price. Assembly languages have many disadvantages, not the least of which are higher software development costs and a lack of code portability. C++ is an object-oriented superset of C that is increasingly popular among embedded programmers. All of the core language features are the same as C, but C++ adds new functionality for better data abstraction and a more object-oriented style of programming. These new features are very helpful to software developers, but some of them reduce the efficiency of the executable program. C++ tends to be most popular with large development teams where the benefits to developers outweigh the loss of program efficiency. ADA is also an object-oriented language, though substantially different from C++. ADA was originally designed by the US Department of Defense for the development of mission-critical military software. Despite being twice accepted as an international standard, ADA 83 and ADA 95, it has not gained much of a foothold outside of the defense and aerospace industries. It has been losing ground there in recent years. This is unfortunate because the ADA language has many features that would simplify embedded software development if used instead of C or C++. ADA's emphasis on readability and reliability is in contrast with the C family of languages, including C++. Java detects buffer overrun errors, but its weakly typed primitive type facility allows data misuse errors that would be caught in ADA, unlike both Java and C-based languages. ADA is seeing significant usage worldwide in high integrity, safety critical, high security domains, including commercial and military aircraft avionics, air traffic control, railroad systems, and medical devices with its embodiment of modern software engineering principles. Significant language features: packages, data types, data objects, and procedure specifications can be encapsulated into a package. This supports the program design of data abstraction. Exception handling. ADA has very good exception handling capabilities which allow the program to handle its own runtime errors. Generic program units. It is possible to write a procedure, for example a sorting procedure, which does not require a data type to be specified. Parallel or concurrent processing. ADA supports parallel and concurrent execution of tasks. Desired language characteristics. A developer writing software at the application level doesn't know how a string gets output to the display. It happens when a particular routine is called with the proper parameters. The various desired language characteristics were hardware knowledge, efficient code, peripheral interfaces, robust code, minimal resource, reusability, development tools. C, currently the most popular language used, lacks support for embedded software development, makes direct use of very low-level POSIX threads, little support for abstraction and exceptions. Java, de facto standard for programming desktop applications, explicit support for modules, currency, and exceptions. Problems for embedded software, unpredictability, and lack of direct control real-time. Java tries to overcome. ADA, used in safety-critical applications, programming in the large and code reuse, tasking features for concurrency, high-level exceptions, real-time facilities. A developer writing software at the application level doesn't know how a string gets output to the display. It happens when a particular routine is called with the proper parameters. The various desired language characteristics were hardware knowledge, efficient code, peripheral interfaces, robust code, minimal resources, reusability, development tools, time access and control, exception handling, parallelism and determinacy abstraction, time access and control, mechanisms or primitives for dealing with absolute and real time to control and monitor program timing behavior, basic operations, set a clock or timer, read value of timer object, higher level, instructions to delay a task, generate timeout signals, exception handling, unusual behaviors in both hardware and software should be detected and handled gracefully. Should also be easy to distinguish between unusual and normal ones. Useful language structures, define, test, and recover from exceptions. Desired language characteristics, software management. Embedded software is complex, large amount of code, a variety of activities and requirements. Language features must provide help with key to managing complexity of large embedded systems, that is, decomposition and abstraction. Parallelism and determinacy. Embedded system or real world is inherently parallel. Deadlock and race conditions are a real problem. Is program behavior predictable and repeatable? A problem for parallel systems. Efficient code. Because embedded systems are typically designed with the least powerful and most cost-effective processor that meets the performance requirements of the system, embedded software developers must make every line of code count. The ability to write efficient code is a great quality to possess as a firmware developer. Hardware knowledge. The embedded software developer must become intimately familiar with the integrated circuits, the boards and buses, and the attached devices used in order to write solid embedded software, also called firmware. Embedded developers shouldn't be afraid to dive into the schematics, grab an oscilloscope probe, and start poking around the circuit to find out what is going on. Minimal resource. Along the same lines of creating a more robust system, another large differentiator between embedded software and other types of software is resource constraints. The rules for writing firmware are different from the rules for writing software for a PC. Take memory allocation, for instance. An application for a modern PC can take for granted that it will have access to practically limitless resources. But in an embedded system, you will run out of memory if you do not plan ahead and design the software properly. An embedded software developer must closely manage resources from memory to processing power so that the system operates up to specification and so failures don't occur. For example, using standard dynamic memory allocation functions can cause fragmentation and eventually the system may cease to operate. This requires a reboot since you have no place to store incoming data. Quite often, in embedded software, a developer will allocate all memory needed by the system at initialization time. This is safer than using dynamic memory allocation, though it cannot always be done. Robust code. There are expectations that embedded systems will run for years in most cases. This is not a typical requirement for software applications written for a PC or Mac. Now, there are exceptions. For example, if you had to keep unplugging your microwave in order to get it to heat up your lunch for the proper amount of time, it would probably be the last time you purchased a product from that company. Peripheral interfaces. At the lowest level, firmware is very specialized because Each component or circuit has its own activity to perform and furthermore, its own way of performing that activity. Embedded developers need to know how to communicate with the different devices or peripherals in order to have full control of the devices in the system. Reacting to stimuli from external peripherals is a large part of embedded software development. For example, in one microwave oven, the firmware might get the data from a temperature sensor by reading an 8-bit register in an external analog to digital converter. In another system, the data might be extracted by controlling a serial bus that interfaces to the external sensor circuit via a single wire. Time access and control. Add a comprehensive set of timing packages, calendar and real-time delay function. Java elaborate date class, coarse clock granularity, but real-time Java has access to a nanosecond clock. C standard libraries for interfacing to calendar time. POSIX thread library or pthreads has a nanosecond clock. Concurrency control, inherent feature of embedded systems. Software constructs for defining, synchronizing communication among parallel activities and scheduling their execution. In addition to the above higher level facilities, mechanisms are needed for finer degree of hardware control and timing. For example, declarations or statements that directly deal with interrupts, input, output, etc. Java provides threads and shared memory plus synchronization. C has to incorporate real-time POSIX primitives, fork, wait, spawn, etc. for concurrency. Can have either shared memory or use message passing via MPI. ADA provides tasks and uses a message passing approach. Reusable software, code portability or code reuse writing software so that it can be moved from hardware platform to hardware platform. It is very useful to aid transition to new projects. This cannot always be done. We have seen how individual each embedded system is. Development tool. The tools you will use throughout your career as an embedded developer will vary from company to company and often from project to project. This means you will need to learn new tools as you continue in your career. Typically, these tools are not as powerful or as easy to use as those used in PC software development. The debugging tools you might come across could vary from a simple LED to a full-blown in-circuit emulator, ICE. This requires you as the firmware developer and the one responsible for debugging your code to be very resourceful and have a bag of techniques you can call upon when the debug environment is lacking. Control. Control order in which instructions are executed, program flow. Conditional execution. Execute a set of statements if some condition is met. Select one set of statements to be executed from several options depending on one or more conditions. Iterative execution. Repeated execution of a set of statements, a specified number of times or until some condition is met or while some condition is true. Multitasking and task scheduling. Software simply has a loop. Loop calls subroutines with each subroutine concerned with a part of hardware or software. Interrupts generally set flags or update counters that are read by the rest of the software. Control loop approach. Do, open curly brackets, close square brackets, system, period, delay, open brackets, 100, close brackets, semicolon, scan, open brackets, channel 1, close brackets, semicolon, scan, open brackets, channel 2, close brackets, semicolon, close curly brackets, while, open brackets, true, close brackets, semicolon. Problems. Inaccurate timing, unpredictable response time as more components are added. Even if we add flags to check the occurrence of an event, most of the CPU time will be wasted on polling these flags. Control loop approach is suitable for applications with few deadlines, suitable for very small embedded processors with small resources, not suitable for time deterministic systems. The solution to overcome these disadvantages is multitasking. The various favors multitasking provide are modular approach, divide the overall activity into independent tasks. Tasks can be directly linked with interrupt handlers so that events can directly synchronize with the code. Tasks execution dependent on event occurrence. Activities requiring more attention are assigned to higher priority tasks. There are two types of multitasking which are given below: preemptive multitasking, non-preemptive multitasking. Preemptive multitasking. The term preemptive multitasking is used to distinguish a multitasking operating system which permits preemption of tasks from a cooperative multitasking system wherein processes or tasks must be explicitly programmed to yield when they do not need system resources. Non-preemptive multitasking. Non-preemptive multitasking is a style of computer multitasking in which the operating system never initiates a context switch from a running process to another process. Such systems are either statically scheduled, most often periodic systems, or exhibit some form of cooperative multitasking, in which case the computational tasks can self-interrupt and voluntarily give control to other tasks. Cooperative multitasking. Multiple tasks execute by voluntarily ceding control to other tasks. One defines a series of tasks and each task gets its own subroutine stack. Idle task calls an idle routine. Another architecture used is an event queue, removing events and calling subroutines based on their values. Pros and cons. Same as control loop, except that there is a more modular approach, but due to non-determinism of time factor, not used in embedded systems. Interrupt handling. The kernel serves the interrupts in the context of the interrupted process, even though it may not have caused the interrupt. The interrupted process may have been executing in user mode or in kernel mode. The kernel saves enough information so that it can later resume execution of the interrupted process and services the interrupt in kernel mode. The kernel does not spawn or schedule a special process to handle interrupts. User and kernel mode switching. When a transition between user mode and kernel mode is required in an operating system, a context switch is not necessary. A mode transition is not by itself a context switch. However, depending on the operating system, a context switch may also take place at this time. Preemptive multitasking. Preemptive multitasking, let OS be the boss. Used in most of the embedded system. Time slices allotted to processes. Process is context switched with the next process in the scheduling queue due to the following reasons. The process has consumed its time slice. The system clock interrupt preempts the process. The process goes to wait state, often due to planned sleeping, waiting for an input-output event to happen, or just mutual exclusion. A higher priority process becomes ready for execution, which causes a preemption. The process gives away its time slice voluntarily. The process terminates itself. Time slice. Preemptive multitasking involves the use of an interrupt mechanism which suspends the currently executing process and invokes a scheduler to determine which process should execute next. Therefore, all processes will get some amount of CPU time at any given time. An interrupt is scheduled to allow the operating system kernel to switch between processes when their time slices expire, effectively allowing the processor's time to be shared between a number of tasks, giving the illusion that it is dealing with these tasks simultaneously or concurrently. The operating system which controls such a design is called a multitasking system. Multi-threading. Multiple threads of operation in a single process. Each task shares code and primary data space. Any global variable is accessible to all tasks. Different stacks used by different tasks are the only differentiating factor. Pointers to data items can be used freely in this environment. No need for virtual to physical memory translation. Multiprocessing. Each task has a distinct code and data space. Boundaries are enforced by hardware memory management. Increased overhead due to memory translation and context switching. Essentially, this is desktop computing done on embedded systems, but is necessary for high reliability requirements application. Timing specification. The most important timing specifications for interfacing components to a bus-oriented design are rise or fall time, propagation delay time, setup time, hold time, tri-state enable and disable delays. pulse width, clock frequency. Consider moving some of the more difficult tasks to accommodate tasks to a timer-based interrupt. The interrupt can be configured to operate at a faster rate that accommodates the difficult tasks and frees up the balance of the tasks to operate at a different rate. If a task is moved to an interrupt, communications to and from the task will require either a semaphore or buffer protocol. This is because the task will be completely asynchronous to the other tasks, much as the tasks in a preemptive operating system. Consider using a tick that is smaller than the smallest task timing increment. Sometimes using a tick that is 1/2 or 1/3 of the smallest task timing increment will create integer multiples for hard to accommodate tasks. Exception handling. Exception handling is the method of building a system to detect and recover from exceptional conditions. Exceptional conditions are any unexpected occurrences that are not accounted for in a system's normal operation. It is difficult to protect the system from the effects of exceptional conditions because, by nature, all unusual occurrences cannot be anticipated when the system is designed. Some examples of exceptional conditions are incorrect input from the user, bit-level memory or data corruption, software design defects that cause a system to enter an undefined state, and environmental anomalies. If these exceptional conditions are not properly caught and handled, they can cause an error or failure in the system. Failures due to exceptions are estimated to account for 2/3 of system crashes and 50% of system security vulnerabilities. When designing an embedded system, exception handling is usually focused on software. In fact, more than 2/3 of code written for systems is devoted to properly detecting and handling exceptions. However, most software testing efforts focus on exercising the correct operation of code and not determining how robust it is to exceptional conditions. Therefore, exception handling code is the least tested and most susceptible to bugs. Exception handling techniques can be separated into two broad categories: programmed exception handling, default exception handling. In some cases, programmed exception handling is capable of doing forward error recovery, but both programmed and default exception handling methods can perform backward error recovery. Forward error recovery can mask any exceptional occurrences and continue normal operations. Backward error recovery must halt normal system execution and attempt to return to a previous normal state to continue execution and retry the operation. Checkpointing and recovery is a technique of backward error recovery for tolerating transient or intermittent conditions. In real-time systems, timing and meeting deadlines are the first priority, especially for safety-critical systems. However, if exceptional conditions occur, there must be some detection and recovery mechanisms in place to prevent error propagation. The extent and complexity of the exception handling mechanisms will make it difficult to calculate and meet timing constraints. Exceptional conditions due to design defects are especially dangerous because they will always be present. If you knew about all design defects in a system a priori, they would have been eliminated before building the system. Since we have not yet learned how to design perfect systems, it is important that exception handlers can reduce the impact of the design defects as much as possible. In most cases, default exception handlers cannot do much to continue system operation. In the best cases, they can use the checkpointing and recovery system to mark transient errors, but for truly exceptional conditions that cause error states, the best that can be hoped for is a graceful program termination. In order to achieve robust operation, as much exception handling as possible is desired. However, exception handling overhead may be too great for real-time systems and make timing and scheduling difficult. Separation of detection code from recovery code. A low-level function that detects a failure of some sort should be able to say, "Hang on, we have a problem. Let's abort the current sequence," without knowing how and where the problem will be handled. This is especially important when a function may be called from several places and in different situations, each of which potentially needs different handling. The function must be able to raise an exception, signal that an error has occurred from anywhere within the program, regardless of how deep it is in the call stack. A way to identify which error occurred. In other words, functions that detect exceptions need to say, "Hey, we've got exception A," and functions that do error cleanup and recovery need to say, "If you have got exception A, do this. If you have got exception B, then do that." Unwrapping of the calling stack. If an exception occurs within a sequence of nested functions, A calls B, which calls C, which calls D, etc., execution should stop immediately in each of these functions. The deepest function should return immediately to its caller, which should return to its caller, and so on, until execution has propagated to a function that is high enough in the call tree to handle the exception. Local cleanup. Each of the intermediate functions may need to do some cleanup, release resources, reset its state, and so on. This is necessary since each function has stopped in the middle of execution. The process of raising an exception must leave all parts of the system in a state that will allow recovery by ensuring that no part of the system remains in an inconsistent state. The best way to understand this exception mechanism is to see how it is actually used. The following is an example of a call tree. Function A calls function B, which calls function C, which calls function D. Function D checks and discovers some sort of exceptional condition that it can't handle by itself. Since function D can't recover, it signals its caller, function C, that it has had to abort execution. Similarly, C can't handle the problem. It needs to bounce the problem up to function B. Function B hasn't got the political clout to solve the problem either. So it too signals its caller A. The bug stops in function A. It takes some recovery action and the system carries on execution. High-level language. Each machine instruction typically does little more than, say, add two numbers. So high-level languages aim to specify many instructions concisely and intuitively. Arithmetic expressions are typical. Coding an expression such as ax square plus bx plus c in machine code is straightforward, tedious, and best done by a compiler. The C language provides such expressions, control flow constructs such as loops and conditionals, and recursive functions. The C++ language adds classes as a way to build new data types, templates for polymorphic code, exceptions for error handling, and a standard library of common data structures. Java is a still higher level language that provides automatic garbage collection, threads, and monitors to synchronize them. Embedded Java. The use of Java may be different, however. We anticipate that Java programs for embedded applications will differ from net applets in at least 5 major ways. Embedded applications will be compiled into the native ISA for the target hardware, capable of running in the absence of a hard disk or floppy disk and a network connection, supported by highly tailored, thus relatively small runtime packages, able to execute on multiple processors if needed for capacity expansion, contain significant amounts of legacy C code, at least during the transition from C to Java. Embedded C. Embedded C uses most of the syntax and semantics of standard C. For example, main brackets function, variable definition, data type declaration, conditional statements, if, switch, case, loops, while, for, functions, arrays and strings, structures and union, bit operations, macros, unions, etc. Advantages. It is small and reasonably simpler to learn, understand, program, and debug. Compared to assembly language, C code written is more reliable and scalable, more portable between different platforms. C compilers are available for almost all embedded devices in use today, and there is a large pool of experienced C programmers. Embedded C. Of high-level languages, C is the closest to assembly languages. Most microcontrollers have available C compilers. Writing in C simplifies code development for large projects. It is easier and less time-consuming to write in C language than assembly. C is easier to modify and update. We can use code available in function libraries. C code is portable to other microcontrollers with little or no change. Assembly is the fastest. However, it is difficult to find or train assembly experts. Then, if a new processor is required, we have to start over. ADA. ADA also supports runtime checks to protect against access to unallocated memory, buffer overflow errors, range violations, off by one errors, array access errors, and other detectable bugs. These checks can be disabled in the interest of runtime efficiency, but can often be compiled efficiently. It also includes facilities to help program verification. For these reasons, ADA is widely used in critical systems where any anomaly might lead to very serious consequences, for example, accidental death, injury, or severe financial loss. Examples of systems where ADA is used include avionics, railways, banking, military, and space technology. Though the semantics of the language allow automatic garbage collection of inaccessible objects, most implementations do not support it by default, as it would cause unpredictable behavior in real-time systems. ADA does support a limited form of region-based memory management. Also, creative use of storage pools can provide for a limited form of automatic garbage collection, since destroying a storage pool also destroys all the objects in the pool. It is even possible to declare several different access types that all designate the same type but use different storage pools. Tasks can have entries for synchronization, a form of synchronous message passing. Task entries are declared in the task specification. Each task entry can have one or more accept statements within the task body. If the control flow of the task reaches an accept statement, the task is blocked until the corresponding entry is called by another task. Similarly, a calling task is blocked until the call task reaches the corresponding accept statement. Task entries can have parameters similar to procedures, allowing tasks to synchronously exchange data. In conjunction with select statements, it is possible to define guards on accept statements, similar to Dijkstra-guarded commands. Runtime environment. Embedding the runtime consists of various steps: compiling and linking the mono runtime, initializing the mono runtime, optionally expose C code to the C or CIL universe. The runtime library may implement a portion of the runtime environment's behavior, but if one reads the code of the calls available, they are typically only thin wrappers that simply package information and send it to the runtime environment or operating system. However, sometimes the term runtime library is meant to include the code of the runtime environment itself, even though much of that code cannot be directly reached via a library call. For example, the C programming language requires only a minimal runtime library, commonly called CRT0, but defines a large standard library called C standard library that has to be provided by each implementation. C compiler and cross compiler. Normally, C program building process involves 4 stages to get executable. .exe. Number 1, preprocessing. Number 2, compilation. Number 3, assembly. Number 4, linking. Number 1, preprocessing. The preprocessor takes a C++ source code file and deals with the hashtag includes, hashtag defines, and other preprocessor directives. The output of this step is a pure C++ file without preprocessor directives. Number 2, compilation. The compiler takes the preprocessor's output and produces an object file from it. Number 3, linking. The linker takes the object files produced by the compiler and produces either a library or an executable file. Creating an executable is a multi-stage process divided into 2 components: compilation and linking. In reality, even if a program compiles fine, it might not actually work because of errors during the linking phase. The total process of going from source code files to an executable might better be referred to as a build. Preprocessing. This is the very first stage through which a source code passes. In this stage, the following tasks are done. Number 1, macro substitution. Number 2, comments are stripped off. Number 3, expansion of the included files. The preprocessor provides the ability for the inclusion of header files, macro expansions, conditional compilation, and line control. Many times you will need to give special instructions to your computer. This is done by inserting preprocessor directives into your code. When you begin compiling your code, a special program called the preprocessor scans the source code and performs simple substitution of tokenized strings for others according to the predefined rules. The preprocessor is not a part of the C language. In C language, all preprocessor directives begin with the pound character hashtag. Example, hashtag include stdio period h. This directive causes the header to be included into your program. Other directives such as hashtag pragma control compiler settings and macros. Example, hashtag 1 open quotes hello period C close quotes. Hashtag 1 open quotes build hyphen in close quotes. Hashtag 1 open quotes command hyphen line close quotes. Hashtag 1 open quotes hello period C close quotes. Hashtag 1 open quotes /USR /include /STDIO period H close quotes 134. Hashtag 28 open quotes /USR /include /STDIO period H close quotes 34. Period. Truncated some text period. Extern void fun log file open parenthesis file star underscore stream close parenthesis underscore attribute underscore open double brackets underscore no throw underscore close double brackets semicolon. Hashtag 918 open quotes /USR /include /STDIO period H close quotes 34. Hashtag 2 open quotes hello period C close quotes 2. Int main open brackets close brackets open curly brackets print f open brackets open quotes maximum age colon percentage d close quotes comma 21 close brackets semicolon close curly brackets. In the above code hello.I you can see macros are substituted with its value ma underscore age with 21 in printf statement. Comments are stripped off line 1, line 2 and line 5 and libraries are expanded stdio period H. Compilation. Compilation is the second pass. It takes the output of the preprocessor and generates assembler source code. Compilation refers to the processing of source code files .c, .cc or .cpp and the creation of an object file. This step doesn't create anything the user can actually run. Instead, the compiler merely produces the machine language instructions that correspond to the source code file that was compiled. For instance, if you compile but don't link 3 separate files, you will have 3 object files created as output, each with the name .o or .obj. The extension will depend on your compiler. Each of these files contains a translation of your source code file into a machine language file, but you can't run them yet. You need to turn them into executables your operating system can use. Syntax checking. When an error is detected in the program, the compiler will normally report the file name and line that is preventing compilation. Object code. The compiler produces a machine code equivalent of the source code that can then be linked into the final program. The code itself cannot be executed yet, as it has to complete the linking stage. Cross compiler. A cross compiler is a compiler capable of creating executable code for a platform other than the one on which the compiler is running. For example, in order to compile for Linux or ARM, you first need to obtain its libraries to compile against. A cross compiler is necessary to compile for multiple platforms from one machine. A platform could be infeasible for a compiler to run on, such as for the microcontroller of an embedded system, because those systems contain no operating system. In para-virtualization, one machine runs many operating systems, and a cross compiler could generate an executable for each of them from one main source. Cross compilers are not to be confused with a source-to-source compiler. A cross compiler is for cross-platform software development of binary code, while a source-to-source compiler just translates from one programming language to another in text code. Both are programming tools. The fundamental use of a cross compiler is to separate the build environment from target environment. This is useful in a number of situations. Bootstrapping to a new platform. When developing software for a new platform or the emulator of a future platform, one uses a cross compiler to compile necessary tools such as the operating system and a native compiler. Embedded computers, where a device has extremely limited resources, for example, A microwave oven will have an extremely small computer to read its touchpad and door sensor, provide output to a digital display and speaker, and to control the machinery for cooking food. This computer will not be powerful enough to run a compiler, a file system, or a development environment. Since debugging and testing may also require more resources than are available in an embedded system, cross-compilation can be less involved and less prone to errors than native compilation. Assembling. Assembly is the third stage of compilation. It takes the assembly source code and produces an assembly listing with offsets. The assembler output is stored in an object file. Since the output of this stage is a machine level file, so we cannot view the content of it. If you try to open and view it, you will see something that is totally not readable. The code can be explained as ELF, executable and linkable format. This is a relatively new format for machine level object files and executable that are produced by GCC. Low level tasks that either can be better implemented in assembly or can only be implemented in assembly language. Also, it is frequently useful for the programmer to look at the assembly output of the C compiler and hand edit or hand optimize the assembly code in ways that the compiler cannot. Assembly is also useful for time-critical or real-time processes because, unlike with high-level languages, there is no ambiguity about how the code will be compiled. The timing can be strictly controlled, which is useful for writing simple device drivers. Inline assembly. One of the most common methods for using assembly code fragments in a C programming project is to use a technique called inline assembly. Inline assembly is invoked in different compilers in different ways. Also, the assembly language syntax used in the inline assembly depends entirely on the assembly engine used by the C compiler. Microsoft C++, for instance, only accepts inline assembly commands in MASM syntax, while GNU GCC only accepts inline assembly in GAS syntax, also known as AT&T syntax. Advantages of inline assembly. Short assembly routines can be embedded directly in C function in a C code file. The mixed language file that can be completely compiled with a single command to the C compiler, as opposed to compiling the assembly code with an assembler, compiling the C code with the C compiler, and then linking them together. This method is fast and easy. If the inline assembly is embedded in a function, then the programmer doesn't need to worry about #calling conventions, even when changing compiler switches to a different calling convention. Linking. Linking refers to the creation of a single executable file from multiple object files. In this step, it is common that the linker will complain about undefined functions, commonly main itself. During compilation, if the compiler could not find the definition for a particular function, it would just assume that the function was defined in another file. If this isn't the case, there is no way the compiler would know. It doesn't look at the contents of more than one file at a time. The linker, on the other hand, may look at multiple files and try to find references for the functions that weren't mentioned. The compiler does its thing and the linker does its thing. By keeping the functions separate, the complexity of the program is reduced. Another, more obvious advantage is that this allows the creation of large programs without having to redo the compilation step every time a file is changed. Instead, using so-called conditional compilation. It is necessary to compile only those source files that have changed. For the rest, the object files are sufficient input for the linker. Conditional compilation. This makes it simple to implement libraries of pre-compiled code. Just create object files and link them just like any other object file. The fact that each file is compiled separately from information contained in other files, incidentally, is called the separate compilation model. A linker is something that allows blocks of code to be compiled separately. This can speed up the overall process of building code and allows some flexibility with how the blocks are later used. In other words, they can be relocated in memory. For example, adding 1000 to every address to scoot the block up by 1000 address cells. To get the full benefits of condition compilation, it is probably easier to get a program to help you than to try and remember which files you have changed since you last compiled. You could of course just recompile every file that has a timestamp greater than the timestamp of the corresponding object file. Knowing the difference between the compilation phase and the link phase can make it easier to hunt for bugs. Compiler errors are usually syntactic in nature, a missing semicolon, an extra parenthesis. Linking errors usually have to do with missing or multiple definitions. If you get an error that a function or variable is defined multiple times from the linker, that's a good indication that the error is that two of your source code files have the same function or variable. Common errors during this stage are either missing functions or duplicate functions. Linker errors can also come about in functions that you have declared and defined if you fail to include all of the necessary object files in the linking process. A sometimes subtle error is when the linker complains about there being more than one definition for a class, function, or variable. This issue can come up in one of several ways. First, there might actually be two definitions of an object. For instance, two global variables, both declared as external variables to be accessible outside of the source code file. This is a legitimate concern for both functions and variables, and it definitely can happen. The last bizarre type of linker error is a complaint about an undefined reference to main. Debugging. Debugging is one of a series of steps necessary to produce quality software. Debugging is a methodical process of finding and reducing the number of bugs or defects in a computer program. Testing exercises the capabilities of a program by stimulating it with a wide range of input values. First, the program is tested under normal conditions. If it appears to work, its handling of special cases and boundary conditions is tested. Tests should be carefully engineered to force execution of all program branches and thus ensure that every decision node is executed correctly. Any peculiar performance by the program during testing is considered a potential bug and should be investigated. Stabilization, the second phase, is an attempt to control conditions to the extent that a specific bug can be generated at will. Usually, a given set of test conditions will cause a bug to appear, and the bug will remain even when statements are added in the source code. Localization involves narrowing the range of possibilities until the bug can be isolated to a specific variable or segment of code. Debugging tools are needed in different platforms to identify and fix bugs in the system, for example, logical or synchronization problems in the code or a design error in the hardware. To collect information about the operating states of the system that may then be used to analyze the system, to find ways to boost its performance or to optimize other important characteristics, for example, energy consumption, reliability, real-time response, etc. An in-circuit debugger, ICD, a hardware device that connects to the microprocessor via a GTAG or Nexus interface. This allows the operation of the microprocessor to be controlled externally, but is typically restricted to specific debugging capabilities in the processor. An in-circuit emulator, ICE, replaces the microprocessor with a stimulated equivalent, providing full control over all aspects of the microprocessor. A complete emulator provides a simulation of all aspects of the hardware, allowing all of it to be controlled and modified, and allowing debugging on a normal PC. The downsides are expense and slow operation, in some cases up to 100 times slower than the final system. For SoC designs, the typical approach is to verify and debug the design on an FPGA prototype board. Tools such as Certus are used to insert probes in the FPGA RTI that make signals available for observation. This is used to debug hardware, firmware, and software interactions across multiple FPGA with capabilities similar to a logic analyzer. Debugging by printing. The most common debugging technique is monitoring, which in applications programming is done by calling printf at suitable points. When you are debugging kernel code, you can accomplish the same goal with printk. One of the differences is that printk lets you classify messages according to their severity by associating different log levels or priorities with the messages. You usually indicate the log level with a macro. For example, kern_info, which we saw prepended to some of the earlier print statements, is one of the possible log levels of the message. The log level macro expands to a string which is concatenated to the message text at compile time. That's why there is no comma between the priority and the format string in the following examples. Here are two examples of printk commands, a debug message and a critical message. Printk, open brackets, kern underscore debug, open quotations, here I am, colon, percentage, s, colon, backward slash n, close quotes, comma, underscore file, underscore comma underscore line underscore close brackets semicolon. Print k open brackets kern underscore crit open quotes I am thrashed semicolon giving up on percentage p /n close quotes comma ptr close brackets semicolon. Debugging by querying. A massive use of print k can slow down the system noticeably because syslog_d keeps syncing its output files. Thus, every line that is printed causes a disk operation. This is the right implementation from syslog_d's perspective. It tries to write everything to disk in case the system crashes right after printing the message. However, you don't want to slow down your system just for the sake of debugging messages. This problem can be solved by prefixing the name of your log file as it appears in the /etc/syslog_d conf with a minus. The problem with changing the configuration file is that the modification will likely remain there after you are done debugging, even though during normal system operation you do want messages to be flushed to disk as soon as possible. An alternative to such a permanent change is running a program other than klogd, such as cat or proc or kmsg as suggested earlier, but this may not provide a suitable environment for normal system operation. Debugging by watching. Sometimes minor problems can be tracked down by watching the behavior of an application in user space. Watching programs can also help in building confidence that a driver is working correctly. For example, we were able to feel confident about Skull after looking at how its read implementation reacted to read requests for different amounts of data. There are various ways to watch a user space program working. You can run a debugger on it to step through its functions, add print statements, or run the program under strace. The strace command is a powerful tool that shows all the system calls issued by a user space program. Not only does it show the calls, but it can also show the arguments to the calls as well as return values in symbolic form. When a system call fails, both the symbolic value of the error, for example ENOMEM, and the corresponding string out of memory are displayed. strace has many command line options, the most useful of which are -t to display the time when each call is executed, -t caps to display the time spent in the call, -e to limit the types of calls traced, and -o to redirect the output to a file. By default, strace prints tracing information on stderr. Debugging by default. Sometimes bugs remain in the driver and the system faults when the driver is executed. When this happens, it's important to be able to collect as much information as possible to solve the problem. Note that fault doesn't mean panic. The system can panic, and it may if a fault happens outside of a processor's context or if some vital part of the system is compromised. But when the problem is due to a driver error, it usually results only in the sudden death of the process, unlucky enough to be using the driver. The only unrecoverable damage when a process is destroyed is that some memory allocated to the process's context is lost. For instance, dynamic lists allocated by the driver through KMALLOC might be lost. However, since the kernel calls the close operation for any open device when a process dies, your driver can release what was allocated by the open method using GDB. GDB can be quite useful for looking at system internals. Proficient use of the debugger at this level requires some confidence with the GDB commands, some understanding of assembly language for the target platform, and the ability to match source code and optimize assembly. Useful task that GDB performs on the running kernel is disassembling functions via the disassemble command, which can be abbreviated to disas, or the examine instructions X or I command. The disassemble command can take as its argument either a function name or a memory range, whereas X or I takes a single memory address, also in the form of a symbol name. You can invoke, for example, X bar 20i to disassemble 20 instructions. Note that you can't disassemble a module function because the debugger is acting on VM Linux, which doesn't know about your module. Numerous capabilities normally provided by GDB are not available when you are working with the kernel. For example, GDB is not able to modify kernel data. It expects to be running a program to be debugged under its own control before playing with its memory image. It is also not possible to set breakpoints or watch points or to single step through kernel functions. Program validation and testing. Validation and verification (V&V) activities can and should be executed in parallel to all occurring system and software development phases. As always, it is understood that earlier an error is detected, the lower the cost of its elimination will be. Validation checks a problem solving against the requirements as stated by the customer. The aim is to prove that the solution is adequate regarding the customer's requirements. Validation requires to consider real application conditions of the object under analysis. Thus, validation includes that the contractors, the developers, check whether they are developing exactly the product which was ordered by the customer. The validation of the module requirements must be performed in the system context anyway. And since the test and validation must be done in the end at system level also, a natural question too is how much of the tests should be developed or performed independently at module level and how much using the system context. This question has a pragmatic and economic motivation. The cost of developing and maintaining tests for many complex modules is often overwhelming. This is especially striking for complex modules, that is, modules having hundreds of input and output signals. Instead of specifying test vectors and sequences with plausible value combinations for hundreds of signals, it is easier to record such vectors in a C system. As embedded software becomes more complex, its functions become more difficult to test and verify. The verification and validation overhead and cost of fixing of defects and implication of defects that were not detected on time threaten to wipe out all the benefits that software provides. Code verification determines correct behavior of the model for production code generation and of the generated code. Distribution of the effort in design verification and code verification allows an early start to the process, more focused testing, and shorter time to fix the problems. Methods for design verification and code verification include model testing in simulation, software in the loop testing, processor in the loop testing, hardware in the loop testing. Changes require a verification process that ensures the change introduced in the model for production code generation doesn't change the model's behavior. Model testing. Unlike static designs, an executable specification can be evaluated in simulation. Typically, this is done by changing model parameters or input signals and by reviewing the outputs or responses. The behavior of software functionality captured in simulation must meet the expectations specified in requirements. Testing methods where inputs to the software model are created with help from other models are sometimes referred to as model in the loop testing. The term in the loop comes from control systems where there is feedback between an embedded controller and the device being controlled. A model not only includes the software's functional design but also the controller's environment, links to higher level requirements, test vectors, and expectation results. This becomes an executable specification. Results of model testing in simulation verify that software behavior is correct and that it validates the requirements used as the starting point of the development process. Information collected through simulation becomes the benchmark for code verification. Software in loop. This type of verification is particularly useful when software components consist of a mix of generated code, for example, updates to meet new requirements, and handwritten code, for example, existing drivers and data wrappers that may be necessary for execution on the target platform. SIL testing is also used for verification when existing algorithms are reused in graphical models. Some legacy code, while correct, may be difficult and expensive to maintain, and it makes sense to re-implement and verify it in a graphical environment. In this case, models and simulation are the test framework for comparison of outputs of the new model implementation. Processor in the loop. A good starting point for the verification of compiled object code on the target platform is to ensure functional equivalence of code running on the target processor related to the model behavior captured in simulation. Conceptually, processor in the loop (PIL) testing is similar to SIL. The key difference is that during PIL, code executes on the target processor or on an instruction set simulator. The data passed between the model and the deployed object code use real input-output. The SIL model can be reused as a test execution framework for the processor board. With PIL, tests are executed with the embedded algorithm compiled and deployed on the target processor board, and with the existing executable specification. Besides tests for functional equivalence, PIL also lets us step through the assembly level instructions in the debugger and to analyze code compiled, linked, and deployed as it will run on the real system. With PIL, we can review the order in which code functions execute, as well as verify calls to OS functions or other libraries required for the execution on the target. The memory footprint can also be reviewed. In some projects, PIL is an opportunity to compare algorithm behavior on processor boards that meet the same spec, but which come from different vendors. Back-to-back tests. Compare simulation traces from MIL or SIL to traces that use the target embedded processor and pinpoint differences that require manual revision. They are used as a proof that model properties can be transported to properties of the target electronic component. This method is often used as an add-on to model-based test generation methods. Limitation. If the model-based test generation neglected system-level requirements, so will the back-to-back test do. Human-specified tests plus test automation. In short, this is usually known as test automation. Test scenarios are specified in a scripting language, for example Python, or a graphical notation. A test automation tool translates the specification in code that stimulates and checks pass or no pass conditions on MIL, SIL, or HIL simulation platforms. The method applies for the module level as well as for the system level testing. This is the most used test and validation method nowadays. At system level, as argued before, there are extremely many situations that require testing. The manual test production and maintenance is the bottleneck and does not scale with increasing system complexity. Very often, manual test production is used in conjunction with requirements coverage as a method to assess how many tests to develop. System requirements must be documented, for instance, using statements such as when, pre-condition, then post-condition. Conclusion. In this chapter, the user has covered the following aspects of programming embedded system: programming languages, use of high-level languages, C, OOPS, Java for embedded systems, programming and runtime environment, program validation and testing.